All right, ladies and gentlemen, we are on our very last section of this chapter, so it's Title 11-3. We're talking about probability distributions today. But at the top, a few definitions we have to tackle first. So what is a random variable? This is just simply a numerical value of a random event. Okay, and we have two different types of random variables. There's discrete and there's also continuous. So a discrete random variable is something that's countable. So it's a countable value. And then if we're talking about a continuous random variable, a continuous, to be continuous means it just kind of, it can take on any value realistically. And typically we're talking about a range of values when it comes to being continuous. So I'm going to give you some examples just to kind of get us started here. But again, we're talking about a range of values. So something that could take on a range of values. For example, if I were to take all of my students in the class and arrange them from, the shortest person to the tallest person. So I'm talking about like heights. Okay, that could be all within a certain range. Maybe the shortest person in my room is 4'4", and the tallest person is 6'5". Okay, so and then we have that range of all those people in between as well. So height is definitely going to be continuous. Weight, obviously, then too. Pretty similar idea. If I arrange everybody, from the smallest to the biggest according to their weight, that would be continuous. If you think about like in track, maybe distance. So, if you're throwing, let's say, the javelin or the discus or something to that effect, we're all going to throw at different distances, right? So that's going to be a range of values. Time as well, if you think about maybe like in a swim meet, okay, people will be finishing in a swim meet all at different times. Once again, taking on a continuous random variable. Okay, so it could be a range of values. So we have to identify down below here, identify if each one is either discrete or continuous. So when I'm asking myself, is it discrete? Basically, I'm asking, can I count this? If you can count it, then it's discrete. If you can't count it, then it's going to be continuous. Okay, if it's something more measurable, I could say too, that would be continuous. So if we're talking about the number of songs found on a random selection of MP3 players, so is that something that we can count the number of songs? Yes, it is. That'd definitely be discrete. The next one, it says the weights of football helmets sent by a manufacturer. So the football helmets, I mean, just even any item realistically, they're all not going to be perfectly the same. It might be off by, 1/100th of a pound or something like that, or 1/100th even of an ounce, something super microscopic and small. So that would definitely be continuous. But any route, I mean, you're talking about weight, right? The weights of football helmets, if you're weighing something, that's going to be continuous. The exact distances of a sample of discus throws, again, if we're talking about distance, that's going to be continuous because we're all going to throw different distances. The ages of counselors at a summer camp. I said that this is discrete, but I guess it kind of depends on how you're looking at it. But I would say discrete because, I mean, you're definitely counting ages, right? If you're counting how old somebody is, then you're counting how far away they are from their actual birth date. So to me, it's discrete, but I could honestly see continuous for that one too. Okay, the number of hits for the baseball players or for the players of a baseball team. So the number of hits, if we're talking about a number, then it obviously has to be discrete. That's something that you're counting then, right? The distances traveled by the tee shots in a golf tournament. Well, again, distance, we're talking about, so that's going to be continuous. So there you go. Okay, so there's discrete versus continuous. So the last part of this section, on the next page, it says theoretical probability distribution. So we've talked about theoretical probability before in the past, and what theoretical probability is, it's basically what you expect to happen. So this is what is expected to happen. So using this chart below, we're going to fill this out. So it says construct a relative frequency table. It says X represents the sum of the values on 2 dice. So if you go across the top here, this first row, this is basically all the different sums that you can get if you roll 2 dice. Okay, so we can get a 2, we could get a 3, 4, all the way up to 12, right? If we get 2 6s. So what's the frequency of this actually happening? Well, you kind of have it all outlined for you down below too. So the frequency of getting a sum of 2, well, it can only happen one time. And then the frequency of getting a sum of 3, well, I can get a 1 with a 2 or a 2 with a 1. So 2 times. And then the sum of 4 is going to happen 3 times. Sum of 5, we can get that 4 different ways. Sum of 6 would be 5. Sum of 7 is 6. Then it just goes back down the other side, all the way down to 1. Okay, so what is this as a relative frequency? So as a fraction, as a ratio, as a relative frequency, let's see, 1 over 36, right? Because there's 36 total different possibilities that we could roll, and only one of those is going to give us a sum of 2. Okay, and the next one would be obviously 2 out of 36, but that reduces to 1/18. The next one would be 3 out of 36, but that would just be 1/12. And then 4 over 36, which would be 1/9. 5 over 36 does not reduce. 6 over 36, that's 1/6. And again, it just goes all on the opposite side as well. So if it's going to be 5 over 36, and then 4 over 36, or 1/9, 1/12, 1/18, and then 1/36. So now the percentage of what these would be as a decimal, so if you just take your numerator divided by your denominator, so 1 divided by 36, you should get about 0.03. 1 divided by 18 is about 0.06. And then this would be 0.08. This one is 0.11, 0.14, 0.17. And then again, just copying over on the other side, 0.14, 0.11, 0.08, and then 0.06, 0.03. Okay. So now what we're going to do is we're going to actually graph this out, graph the theoretical probability distribution. So these are the percentages that you see over here on the left-hand side. That's your y-axis. And then going across the bottom, these are just all the different sums that we can get. All right, and you're going to kind of see something cool happen once we have this all plotted out. Okay, so I'll kind of explain exactly what that is in a second. But the sum of 2, again, the percentage was 0.03, so that's going to be somewhere about right here. And then getting a sum of 3 was about 0.06. That's going to be just a smidge above, about right here, I'm going to say. Sum of 4 was 0.08, so it's going to be a little bit below 0.10. And then getting a sum of 5, let's see, that was 0.14. Or where am I at? Getting a sum of 2, 0.06, 0.08. Getting a sum of 5, sorry, that's 0.11. I skipped one, I knew I did. So this would be about right here. Getting a sum of 6, that was 0.14. Let's get a little bit closer up here. And then this is obviously where it's going to peak at, 0.17. So I'm going to say that's about right here. And then it just obviously, again, it's going to replicate on the opposite side. So just kind of match where you put that X on the other side. Kind of balance this out as best you can. Doesn't have to be exact. We're just kind of estimating where these would be. Okay. All right, so what you see right here, once your data is all graphed out, this is what's known in statistics as being the standard bell curve. Okay, so if you go on to farther or further math classes, you know, more advanced into stats or anything like that, it's just a way that we always reflect back on. It's something that we use in statistical analysis when it all comes down to it. So you'll probably hear that again in the future, again, if you do continue on to a stats class of some sort. Okay? So we're going to pretend now, so we also want to decipher between theoretical versus experimental probability. So experimental, again, experimental probability distribution, what this is, it's the probabilities that you get from actually conducting an experiment. So this is the probability after conducting an experiment. So when we do an experiment, we record our results, you know, we do our analysis, then this is what we get, right? So that's our experimental probability. So similar idea as the previous problem. This is the different sums that we can have, right? These are all the different sums that we can get, 2 through 12. That's the first row. This is how many times we got that sum. So we're just going to pretend like we did this experiment. Okay, we rolled 2 dice and we got a sum of 2 exactly 2 times. A sum of 3, we got it 5 times. A sum of 4, we got it 6 times, 13 for 5, so on and so forth. I mean, you can see though that in the middle, this is where it peaks, right? We got a sum of 7 22 times. Now we have to try and figure out what's the percentage of this. Well, we have to know how many times did we actually do this experiment. So if you add up all your trials, going straight across here, it actually all adds up to being 100. So we did this experiment 100 times. We rolled 2 dice 100 times, and this is what we got. Okay, so as a percentage, what would this be? Well, that makes the math pretty easy because, I mean, 2 divided by 100, that's obviously just going to be 2%, 0.02. This would be 0.05, 0.06, 0.13, 0.14, 22. Okay, so here's all of my percentages now. All right, so now we're going to graph this out and you can kind of compare it then to the theoretical. Okay, so if we plot out these points, again, we got a sum of 2, 0.02 was that percentage, so just a smidge below. Sum of 3 was 0.05, so it's going to be exactly on the line. 4 was 0.06, so just a smidge above. 5 was at 0.13. So that's going to be about right here, I'm going to say. Sum of 6, we got it 0.14, so just a little below. 7 again is where it peaked at, it was 0.22, so a little bit off the graph even, if you will. And then for 8, it was 0.12, so that's going to be about right here, I'd say. Sum of 9 was 0.11, so that's going to be about right here. Sum of 10, that was 0.08, so about here. Sum of 11, that was 0.03, so about right here. And then 12, we got 0.04. Okay. So if you compare this to the standard bell curve, we're actually pretty right on target. I mean, you can see the overall curve effect taking place, and because of this, this is just kind of introducing us to the last little definition that we have, something known as being the law of large numbers, which basically just says that the more number of trials, in an experiment, the closer your experimental probability is going to be to the theoretical probability. So the more times that you actually do an experiment, the closer and closer your data should be to the actual theoretical. So again, we did this experiment, we're saying 100 times. So if you compare that graph and the info, the data that we got, compare it to the theoretical, like I said, you can still see the overall bell curve. It's a little bit skewed, a little bit off here and there in some places, but overall, I would say we got pretty darn close. But maybe if we did this, if we added more trials to it, maybe if we did it 200 times or maybe even 1,000 times, it would be even more accurate. Okay, so that's basically what all the law of large numbers says. I think we'll also be doing our own experiment to kind of see and test this theory and see how it all works out. But that's it otherwise. All right, so probability and stats, our unit here is over. As usual, if you have questions, don't hesitate to ask us. All right, and have a great day.